Welcome to the 22nd lecture for Physics 4B. This is our first lecture on electromagnetism. That is the start of the one unified theory of both electricity and magnetism. We will start by pointing out the fact that we know quite a bit about electricity and magnetism now. Enough that we can begin to see the silhouette of missing pieces of electricity and magnetism. To highlight this, we start with a scenario illustrating the motion-induced voltage, something we can consider through the Lorentz force law, that electromagnetic force is equal to charge times electric field plus velocity cross product magnetic field. And when we consider the same situation from a different observer's point of view, invoking the principle of relativity, that's where we can see that we need one more law of physics to make our theory of electricity and magnetism consistent with the principle of relativity. And this law is Faraday's law. Faraday's law is the last of electromagnetism laws we need to fully analyze some of the most common and practical electrical devices, the electric motor. So, in the second half of this lecture, we demonstrate some of the devices and work through the analysis of the world's simplest motor. Faraday's law is also the law we needed to cover in order to introduce the last of the linear circuit elements, the inductor. We already talked about capacitors and resistors. We will do that in the next lecture in preparation of our discussion of time-dependent circuits. Let me have you consider this situation. So we've talked enough about electricity and magnetism, right? So this is what we know about electricity and magnetism so far. So we know how to find electromagnetic force given the electric field and magnetic field. So electromagnetic force is given by amount of charge times electric field. So this is the portion that gives you the electric force plus V cross B. Right? This expression looks familiar. So the part that I'm underlining in blue gives you the electric force, and the part that I'm underlining in orange gives you the magnetic force. Right? And this is the combined electromagnetic force. And so we know this, and we know some ways to generate electric and magnetic fields. So the two, or to calculate, find them from the charges. So the two key laws that you have learned are Gauss's law, which gives you a way to calculate the electric field, E dot dA. This net electric flux out of an enclosed surface is equal to Q charge enclosed over epsilon naught. And Ampere's law, that the line integral of magnetic field around the closed loop that we are going to call Amperian loop is equal to some constant times amount of current enclosed. Yep. So I think I might have mentioned this in this class, that the theory of electricity and magnetism is the first complete physical theory that we have developed. It's the crown jewel of classical physics. Like all the other laws of physics you have heard so far, they were sort of disjointed. There's Newton's law of universal gravitation, and you can use them to solve some problem, but it's hard to see them as one unified theory. Theory of electromagnetism is first of that kind. You can actually, this is sort of where we begin to see it, because we have a current that's producing magnetic field. But what is current? It's an electric charge flowing. It's a moving electric charge. So if this was a whole separated thing, then there's no reason for moving electric charge to have any kind of effect on a magnetic field. But we have this relationship that magnetic field can actually apply force on electric charge as long as it's moving. And a moving electric charge can induce magnetic field. So you begin to see some connection between electricity and magnetism. And do people here do puzzles, like 1,000-piece puzzle? Like, so when you're starting out the puzzle, you don't really know how it's going to end up, right? You try to start at some corners and start building it. But once you build enough of it, then you begin to see missing pieces. The empty spot where you kind of know what has to go in there based on what you have. And that's sort of going to be the rest of the semester. Because we know enough about electricity and magnetism, now we can reason to find the missing pieces of law. There's really only one missing law here. Let me write down the third law that you guys technically know. I never wrote it down, but you technically know. So it's this law. It relates to the magnetic flux. It says that net magnetic flux out of an enclosed area is equal to 0. Does this statement make sense? Like, does that sound like that should be true? No, it doesn't sound like it should be true. Why should it be true? Keep guessing. I'm trying to set up something that will help you illustrate it more easily. Why should it be true, intuitively speaking? So it's easier to see with the visualization of magnetic field. So, I have these, right? Let me place a magnet in the middle of that setup. So that you have some illustration of field lines. So that's the magnetic field line that you are used to seeing in different setups, right? So imagine following one of these magnetic field lines. Does it begin anywhere? So, let's say I follow this magnetic field line. Does it begin and end at some point? Or so it goes around the loop, and it's sort of, if you imagine it going through this magnet, it'll sort of enclose a loop on itself. So when you imagine these magnetic field lines, let me just draw a few here. This field line here, this field line here. They all, they never really end anywhere. They simply, go through a loop and then come back to itself. So why is that? Like, why couldn't, here I technically can, if I put this magnet down this way, then it kind of looks like, radially outgoing field lines. But that's not like true in three-dimensional picture. But this kind of field line is something that you would have seen in 3 dimensions with electricity. But why do you not see that with magnetism? So here, you have to imagine these field lines going around this way and then coming back this way. Whereas if it was charged, it was just radially go out all directions. Yeah.
You can have a single charge, but you can have a single volt.
Yeah, there is no such a thing as a single magnetic charge, magnetic monopole. Magnets always occur in dipoles. So that's the way what I wrote down here makes sense. You could almost say what I was beginning to write down here is the magnetic version of Gauss's law. So I might have said, all right, this must be equal to, I'm just making stuff up here. Let's say mu naught times amount of magnetic charge enclosed. Like that could have been true. And for all we know, it is true. Except that magnetic charge, there's no magnetic charge. So the quantity on the right-hand side is something that's always going to be 0. Okay? So we call this Gauss's law for magnetism, or Gauss's law for magnetic field. And this is something that you already know. Once you know Gauss's law for electricity, so you have the sense that electric charges are what's producing electric field that go out radially away from that charge. Then, well, so there will be some similar relationship for magnetic field, except there are no magnetic charges. So the right-hand side here would be 0. Okay? So that's something that you kind of knew, but it was never written down in a mathematical form. And this is what I'm going to tell you. And when we come back from break, we will we'll go through some illustrations to see what's missing. So in this set of laws of electricity and magnetism, there's a missing law here. And I mean, you can guess the name of the missing law. It must be the one that's on the board. Faraday's law. And what I will tell you is that I think Faraday's law probably was discovered experimentally. But what I will tell you is that we can actually theoretically reason it out. We can say, unless this missing law exists, then the laws of electricity and magnetism doesn't make sense. And towards the end of the semester, we are going to do something similar for that one more piece of it. There's a missing term in Ampere's law. And it's called the Maxwell term. That's the last piece of electricity and magnetism that gets completed. And what I'm telling you is that now, from what you know of electricity and magnetism is enough that these missing pieces become obvious when you, well, not become clearer when you look at a particular physical situation that's designed to highlight that. So let's take a little break. That'll give me a chance to set up the demo that I forgot. So this is just a coil of wire. It's nothing special. It's just like the other coil of wire. All it is a copper coil. And so you have seen oscilloscope before, and you have some understanding that what the oscilloscope is supposed to show is a voltage as a function of time. X-axis is time, and the voltage is the y-axis. You have seen all of that before, right? And so what it is measuring right now is voltage change across this coil of wire. What do you expect that to be? 0, right? It's a conductor. Should be at the same voltage. And when I shake it, it doesn't really change all that much, right? I mean, all of that is as expected. Now, this is what I want to show you, that once you have a magnet in play, then it changes. So do I need to? I think I need to put the right amount of exposure where you can see both the coil and the signal on the oscilloscope. So what I'm going to do is I'm going to put this magnet on some ground somewhere. So, you know, even though you can't see it, you can kind of visualize that there's a magnetic field coming out of this, like a very strong dipole magnetic field. And when I move this, within the magnetic field, something interesting happens with that electric signal. So when I drop it, it went down, right? And when I pull it out, then the voltage goes up. And it's directional. So if I change these two connections around, then this time when I push it down, then the voltage will go up. When I push it down, the voltage goes up. When I pull it out, the voltage goes down. So, okay, where is that coming from? So this is what your textbook calls motional EMF. And I've been trying to get rid of that word EMF. So what I'm trying this semester is motion-induced voltage. So let's try to understand how that's happening here. What I'm telling you is that you already know everything you need to know to understand this motion-induced voltage. It's just a case study of something that you already know. Motion-induced voltage. So in this particular setup, what you have is you have a very strong magnet which is generating magnetic field. Let's just say the upper end is the north end, then there's a pretty strong magnetic field coming out of here. And I guess if I'm drawing the field correctly, then it should look like, well, it should look like a dipole field. This is the magnetic field from this strong magnet. And what you are seeing is that when I move a coil of wire, so let me just illustrate with this 3-coil wire thing. I mean, my actual coil has more, but when I take this coil of wire and either move it up or down, that generates voltage. So when I take this and either move it up or down, then when I hook up something to one end and the other and measure this with a voltmeter, then I actually measure a difference in voltage here. Whereas when I didn't have magnet, there was no voltage difference. When I don't have this magnet, then I can move it down all I want. I can move it down all I want, but there will be no voltage generated. It's only when there's this magnet here that you see voltage generated. So the magnet must be playing some role. So how does this presence of magnetic field generate voltage around this loop? Like, how would you begin to analyze that? What kind of things does voltage involve? Not difference in electric field. Okay, so voltage is electric potential. So if you're looking at difference in voltage, there is difference in electric potential. But how is that difference in electric potential related to other quantities? You should remember at least 2 different ways that voltage is related to other quantities. This is something that you should have memorized as a matter of definition.
Change in voltage from A to B, the integral from A to B, electric field.
Yeah. So that's the definition of voltage. That whenever you see voltage difference, that means there's an electric field. Not change in electric field, but an electric field. So that if you integrate the line integral E dot dl from point A to B, well, that is a voltage. Oh, there's a minus sign here somewhere. But whenever you have non-zero voltage, that means that there's some kind of electric field. And the other relationship was relating to energy. But actually, this is what I want to look at. So this is what you are seeing here. That the fact that you see voltage difference there, as I move the coil up or down, means there's something equivalent to an electric field within this coil of wires as I move it up and down. But there's no battery here, so there's nothing that's actually providing that electric field. So there's something that's equivalent to electric field, but not quite an electric field. Have you seen any quantity that's equivalent to electric field? As in, it does similar things that electric field can do, but it's not an electric field. What have you seen? Magnetic field, not just the magnetic field by itself, but V cross B. This can act like electric field. Do you know why? Do you know how I know? It's being added to electric field, which means grammatically, these two must be on the equal footing. Right? It works both in grammar and math. You do not add the 2 things together unless they are same in kind. Like they have to have the same unit, they have to essentially be doing the similar things. So yeah, this is V cross B. So this is what's called, your textbook calls it motional EMF. Or I guess you have to do the line integral of that to get the motional EMF. But this is related to, it's related to what I'm going to try calling motion-induced voltage. So that's, I guess, what I want to analyze here, that as I move this up or down, that there's some direction of the V cross B that I can analyze this as well. As I go around this loop, each time I go around, it adds up, so that I should get something, that can be measured as a voltage by oscilloscope. So let's, for convenience's sake, let's say this coil, I'm going to have it move up with some velocity V naught. All right. So I'm imagining the electric charges that are inside the wire. Let's just, for simplicity's sake, let's imagine they are positively charged. And they are not negatively charged, but I'm not talking about Hall effect, so I can just imagine they're positively charged. What's the direction of V cross B? For one, actually, what's the direction of magnetic field? Kevin? Upward, okay. Yeah, that's an easy thing to observe for now. So we'll start out with it. So let's say we see that magnetic field is mostly upward, right? So that's why Kevin said upward. So let's just analyze it on that basis. Let's say that this magnetic field points up. Then, what do you get for V cross B? Not outward. V is upward, right? Magnetic field is also upward. Yeah, 0. If the two vectors point in the same direction, the cross product is 0. Yeah?
Is the whole thing like one charge that has a velocity? Or is it, because before we were doing that, it's like the velocity was in the direction of the current, right?
Yeah, but here there's no actual current. I'm just physically moving it upward.
Oh, okay.
So the velocity of charge is the same velocity as the velocity of the coil.
Okay.
Yeah. Yeah. All right, so yeah, it doesn't work. So that means, I think actually if you look at this magnetic field lines carefully, you can see that, okay, in the middle they are straight up, but as you go out, it's not straight up. It's, look at this one that I've drawn here. It actually goes a little bit to the side, which means there's a longitudinal part and there's a perpendicular part. So, take this entire direction of a magnetic field. And when you do V cross B, what's the direction of the V cross B? Here, into the board, right? So I guess this is what I do like. When I come around here, I want my V cross B to be out of the board. Because then as you go around the loop, the effect will be adding together. Is that the case? Yeah, V cross B. So this is the direction of magnetic field. So V cross B is out of the board. So, and as you imagine going around the entire loop, if you're looking down from above, V cross B will be going counterclockwise. So that with each one of these loops, they add up. Okay? So yeah, so what that means is, so V cross B is going along the direction of the loop. So if you take the line integral along the loop, if you imagine doing something like this, you will get voltage. And that's the motional voltage that you are seeing being measured by the oscilloscope. Yeah? So this is interesting, but ultimately, I didn't teach you anything new. It's just the application of something that you already knew. Right? And I promise that we can use this to figure out that there's a missing law of electromagnetism. So let me show you a slightly different version of this effect. So the slightly different version looks like this. The coil is sitting there. It's not moving. And what I'm going to do is, instead of moving the coil, I'm going to move the magnet. So let me put it on a stick so that it's easier to move. I'm going to stick the magnet either in or out. So you see voltage there, right? Now, would you have expected to see that voltage? Yeah, kinda. You could have expected it. If how many here are familiar with the principle of relativity? Kinda, when things, it's the relative motion that matters, not absolute motion. So the question of when you look at these two approaching each other, question of which is stationary. That's an academic question. That's a question without a physical meaning. Because in the reference frame of this magnet, it's the coil that's moving. That's what you saw before. But imagine you are the observer on the coil. Then it's the magnet that's moving. So considering the principle of relativity, you could have theoretically expected the effect that you are seeing experimentally there now. When you have this magnet that's moving, that generates voltage. But the coil itself isn't moving. Now, this is what I want you to look at. Look at all the laws of physics that you know. So this time, there's no wire that has any kind of velocity. Here, velocity is 0. The only thing that has velocity is the magnet, but I'm not really looking at the force on the magnet. I'm looking at the force on the things inside the wire. So velocity is 0 for whatever it is you are looking at. And you want to get something that's close to motional EMF. So as you look at this, is there anything here that says if you have a changing magnet? So, when I move this up and down, this is what it does. It changes the magnetic field. So when I move this magnet around, this is what I'm doing. Closer to the magnet, magnetic field is stronger. Farther from the magnet, magnetic field is weaker. So as I move the magnet up and down, I'm changing the strength of magnetic field at the location of this coil. Right? So the question comes down to, is there anything in our law of physics that says when the magnetic field changes, there must be voltage? Right now there isn't, right? But so this is where you have to assume that something like Faraday's law exists. Because other than the fact that you see an experiment, you also can reason it through. That you consider this picture, stationary magnet and moving coil, and that has to be physically equivalent to stationary coil and moving magnet. And when you take the laws of electromagnetism as it's written here, those two are not, they are not symmetric. So when you look at moving coil, something interesting should happen. But when you look at moving magnet, well, nothing interesting should happen when your physical intuition says that both of those are the same physical picture. In fact, if you want to make it symmetric, they can be moving towards each other. Yeah? So this is the Faraday's law, which resolves this paradox, which makes laws of electricity and magnetism consistent with what we expect and what we see in experiment. So let me write down Faraday's law. It says, it actually looks quite similar to Ampere's law, which kind of makes sense because it's a law that relates to the voltage. So this is what Faraday's law says. The line integral of electric field, E dot dl, and this line integral is around the closed loop. So when you do a line integral around the closed loop, so do you guys remember what kind of geometric object a closed loop also define? Like if you have a closed loop, all right, great, you have a closed loop, but you have one other geometric object from this. Surface that's enclosed by this loop, right? So once you have a surface, then you can define a flux, right? So that's how we did it for electric flux here. So we can do the same thing for magnetic field. So with this loop that we have for, call it Faraday's loop, I think we still call it Ampere, whatever. With this closed loop, you can define a surface. So you can look at magnetic field going through the surface and calculate the magnetic flux. So, so let me just write down that definition of magnetic flux. So the magnetic flux, we use this symbol, capital Phi, subscript B. All this means is it's the surface integral of B dot dA over some surface. It doesn't have to be closed, it can be open. If it's a closed surface, then it's like the Gaussian surface that we are using. If it's open surface, then it's like the open surface that's bounded by this loop. Yeah. So what Faraday's law says is that there's a relationship between this line integral of electric field and this magnetic flux coming from the magnetic field. And it's not just, it's a different type of relationship than what you have seen before. So, so right now there's a magnetic flux going through the loops of this wire. But you don't see any voltage there, right? You only see the voltage when the magnetic flux changes. So here, this voltage is going to be related to magnetic flux this way, minus the rate of change of the magnetic flux. Yeah? So there's a time derivative here. So far, in specifying all of this, there wasn't really time derivative. I guess you could have put in some time derivative with the current, but we didn't. So this is Faraday's law. So I guess I made the box too big. So this is Faraday's law. This is what makes this picture consistent, that whether the magnet is the one doing the moving or the coil is the one doing the moving, the effect of either happening is the same. Yeah? Now this picture is a little bit difficult to analyze in detail because the magnetic dipole field is complicated, and so let me give you a simpler picture that I don't have any demo for, but it's a simpler picture to analyze. Let's just see that in this simpler picture, both Faraday's law and motion-induced voltage gives you the exact same result. So this is the classic picture involving this. So let me imagine a field or a space that's filled with magnetic field. Sorry, too many fields. Let me draw it. So this is what I'm imagining. I have magnetic field. Let's say it's coming out of the board. I have magnetic field coming out of the board, but here's something a little bit special about this. There's an abrupt change. There's a boundary. So to the right-hand side here, the magnetic field is some, constant value. Let me call it P not G hat. So our axis would be X, Y, and Z. Okay? So the right-hand side of this boundary, you have this uniform magnetic field. The left-hand side of the boundary, you have no magnetic field. So left-hand side of the boundary, your magnetic field is 0. Good? So this is what I want you to imagine. Imagine that I have a conducting loop. Let me make this easy for myself. Conducting loop of square shape or rectangular shape. Let's say I have a conducting loop that's of some width. So of some width W and of some, I guess the way I'm drawing it looks like height H. Good? And this conducting loop is moving. It's moving at some speed V naught. And we are just going to say, for the purpose of this initial discussion, that somebody is making sure that this loop is moving at this speed. Good? All right. So what do you think should happen with this conducting loop? There should be movement of charge induced in it. Yeah. So let's look at all these segments. Everything that's out here, there's nothing happening to the charges, right? Because they are outside the magnetic field. So the region that would be interesting to look at is this region, the region that's inside the magnetic field here, and this region here. Call it regions 1, 2, 3. In regions 1 and 2, in what direction are the charges being pushed to? Let's once again imagine those are positive charges. What direction are they being pushed? So in region 1, V naught cross B, so downward, right? So there's a force on the charges that's pushing it downward. Okay, that's not going to do anything. I mean, it might, yeah, that's not really going to do anything. And in region 2, it's the same thing. V naught cross B, downward. All right, so the charges might accumulate on one side of the wire, but beyond that, nothing will really happen. What about region 3? It's still downward. So the difference here is that when you have downward V cross B, then this will act like an electric field. Right? So what you have is, if you imagine a path that's going along this conducting loop, then I have this amount of path length here, which will, at every point along this path, will be this value of V cross B, or with this value of V naught times B, because times B naught, because they are perpendicular, uniform, same value throughout, right? So, so the effect of this is going to get added up over this entire length. So if you calculate this, the line integral, if you want to call it, V naught B naught times dl. This is the motion-induced voltage. There's a voltage difference from here to here. So I guess this must be a, sorry, I keep forgetting which is lower and which, well, this is the direction that the charges are moving. The charges moving this way, it'll push the charges here, so there will be a loop current induced in this whole thing. So you could say, this is what you can end up saying, that we can compare to the other thing later, that when you imagine going around this loop, as you go around this loop, there's a voltage difference of V naught B naught times the line integral. That sounds like the H. So there's a voltage difference of V naught B naught H. So all I have to give you now is what is the resistance of the wire. Then take the voltage, divide by the resistance. That'll give you the current. Okay? Good. Everyone okay with that? So that's just using this concept of motion-induced voltage. Once again, no new laws, something that you already know. Now what I want to demonstrate is, do we get the same result using Faraday's law? Well, let's give it a try. So this would be how this picture will be changing. So before, this is the picture that I was trying to sketch. That imagine this oscilloscope is the region with the magnetic field. Then what I was describing was this loop moving from right to left to right, right? And now, for the purpose of applying Faraday's law, what I want to say is, well, maybe it doesn't move that way. Maybe I'm in the reference frame of this loop, and it's this region that's moving. So for this change the picture, this is what you have to imagine. We have to imagine that, what color? Let's use purple. You have to imagine that, okay, the loop is not moving. The loop is stationary. Instead, this boundary is moving to left at speed V naught. Right? So if you are still sticking to Lorentz force law, that doesn't give you anything because there's nothing in this loop that's moving. The sort of the amount of region of space that's filled with the magnetic field is changing. A moment later, this boundary would move up here, and there will be additional region of magnetic field, but the velocity of physical object is 0. So I want to get this result, that the induced voltage inside the loop is still V naught, B naught, H. Let's see if Faraday's law gives us that. So for the time being, let's just focus on the magnitudes. That way I can look at magnitude of the induced voltage is equal to magnitude of the rate of change of the magnetic flux. Good? Let me write down the magnetic flux, an expression for magnetic flux. Guess I can do it this way. Let me give name a parameter. So this distance, or this portion of the width that's filled with the magnetic field, I'm going to call that x. Then magnetic flux, at the very basic level, it's the magnetic field times the area. I mean, there's a whole dot product for you to remember and think about, but here the geometry is simple. Magnetic field comes out of the board, perpendicular to this plane, so this B dot dA business, it's just the magnetic field magnitude times the magnitude of the area. So, all right, so for the calculation here, it's not the area of the entire loop that I'm interested in, it's the area of this portion of the loop that I'm interested in. So I can say, all right, that area is the height, h times x. Okay? So the magnetic flux, I can write it down as a function of x. It'll be magnitude of the magnetic field, B naught, times this area here, h times x. All right? So what Faraday's law tells us is that induced voltage is equal to this thing, or the rate of change of this thing, if you are looking at the absolute value. That's the rate of change of the magnetic flux. You know what? I have an analytical expression. I think I can try taking this derivative. Okay? So I'm going to try to take the time derivative of this entire expression here. B naught h x. Any of these parameters a function of time? B naught a function of time? No. H a function of time? No. What about x? Yeah, the region of space that's filling up, it's going to increase as a function of time. So, all right, let's write it out. It'll be B naught h times rate of change of x. Well, I think I have that. This is my dx dt, right? That's how fast this boundary is moving. So all of that, I get B naught times h times V naught. So this is the magnitude of induced voltage that Faraday's law gives you. Compared to this, oh, it's the same voltage. Same magnitude anyway. Good. Now, let me wrap up the introduction of Faraday's law with this. So, because I have good memory, you will always find me always writing down this minus sign. That's part of the Faraday's law. You forget it, you did something wrong. It's like forgetting this minus sign here. It's one of those serious sign errors. And but the thing is, it's hard to really know intuitively what the effect or the consequence of this minus sign is. That's why we give this minus sign its own name. In your textbook, that minus sign is called Lenz's law. And we have a whole description of consequence of Lenz's law. But what I want to tell you now is that, when you hear Lenz's law, it's not a separate law. It is a part of Faraday's law, but it's this one particular, somewhat abstract part of Faraday's law that we are giving you this word description for, so that you can apply it. When you do it this correctly, you can be sure that you got the directions correctly, and you can kind of forget about this minus sign. But in upper division level work, this minus sign will naturally give you the same result that Lenz's law is giving you. So let me describe Lenz's law, because it's a way to
try to get at this thing that's hard to figure out just purely mathematically because it's too abstract. It comes down to this. So when we use the motional voltage, induced voltage, the result we got is that the current that you would induce, that the current goes clockwise, right? Yes, that's what you got. So it might feel like you got more out of this motion-induced voltage business than you got out of Faraday's law. Because with Faraday's law, put my hand up. I don't know anything about direction. I'm just gonna try to calculate the magnitude. And what I'm telling you is that Faraday's law also gives you the direction. And the direction given by Faraday's law will agree with the direction given by motional voltage, motion-induced voltage. So let me, I guess, write down Lenz's law. It's a bit complicated law. So let me try to state Lenz's law here. Lenz's law. Let's see. So it's related to Faraday's law, where change in magnetic flux induces the voltage, right? And this voltage is going to induce current if it's conducting path, right? All of that is reasonable so far? Okay, so Lenz's law deals with the current. It says that the direction of induced current, that is the current that you would get from the voltage in Faraday's law, it says direction of induced current opposes the change of magnetic flux that induced it. Does the meaning of this clear enough? It's a bit of a complicated sentence. So let me illustrate what I mean here. So here, as this boundary moves to left, when you look at the direction of change of magnetic flux, what direction would you say magnetic flux is changing? Like if you treat magnetic flux like a vector-like quantity. Coming out of the board more, right? Okay. So that's the change in magnetic flux. What Lenz's law tells you is that the induced voltage around this loop, it's going to generate a current. And the current must be generated in such a way that this change is being opposed, meaning the magnetic field due to this loop of current should point into the board. That's going to be opposing this change here, right? So what direction of current should it be? Clockwise or counterclockwise, so that the magnetic field due to induced current opposes this that's coming out of the board. Clockwise, right? So this is a shortcut rule. Clockwise loop of current, magnetic field points into the board. That's the same direction we got with the motional voltage. Yeah, and actually this Lenz's law, it makes a physical sense. In fact, if it was the other way, you'd get a really absurd result. Let me show you why. So let's go back to the initial picture for motional voltage. So this clockwise current, it was set up by this loop that's moving to the right, right? Now, I want you guys to think of the force on this loop, not because of this velocity, but because of this current I that's flowing in this loop, clockwise direction. So what direction is the force on this loop due to this current? Well, I is downward. So this is where you have to use the modified version of the magnetic force. As in, magnetic force on wire is equal to I L cross B, right? So, direction of current cross B. So direction of current cross B. What direction is the force? To the left, right? So because of this current here, there is going to be, how do I draw this? So this is getting very cluttered. Because of that current, there's going to be a leftward magnetic force. What does that do to this initial velocity that it had? Yeah, it's going to decrease, right? It's going to slow down. So this is what you would see physically. And if I could actually set it up, if this is a region of strong magnetic field, and I throw it in here, as it goes through, it's going to slow down. Because as it tries to pass through, there will be a current generated here, and direction of current will be such a way that the I cross B will oppose the direction it's already moving. So it will slow down, come to a stop, and stop. Now, I want you to imagine, what if this was a plus sign? What if Lenz's law was the exact opposite? That the direction of induced current not opposes, but like strengthens the change of magnetic flux that induced it. Like what will happen as this moves into the magnetic field? It'll speed up, so when something moves here, it'll like get launched away. And your intuition says that if something slows down to stop, you can understand it, right? Mechanical energy went into some thermal energy. In fact, if you have a current flowing, it has resistance, you're going to get Joule heating. So it makes sense that you're going to lose mechanical energy. The other picture is just an absurdity, where if it just takes off, where is that energy coming from? And this is the way that you can understand something called eddy current. So let me actually pass this around. Oh, I don't have, well. So I'm going to pass it around. Because there's not enough time per person, I just want you to flip it up and down to see how it behaves as it's, I need one of these.
So that cutout is there so that you can see through the side of the copper tube, and you can see from this end point view that there's nothing special in there. It's a copper tube. It's a tube made of conducting material, the conducting part being important. I'm going to support it vertically, and all the stand stuff, they are I think made of aluminum. They are not ferromagnetic. That's the important. So these are the two slugs. This is one of them that looks like that. And this is the other slug. Also looks metallic. Now, when I drop that, nothing surprising. And let's look at this other slug. So it's sliding down very slowly. And this is the result of Faraday's law and Lenz's law. So what's happening as this slug is sliding down is you have to imagine this slug as a kind of a bar magnet, but maybe a very strong bar magnet. So I forget which end is North Pole, which end is South Pole. For the purpose of illustration, it doesn't matter. Let's say it's North Pole at one end and South Pole at the other end. So that this permanent magnet generates a magnetic field that looks maybe something like this. So as this magnet is sliding down, you have magnetic flux through different, you can imagine different loops. I guess for one purpose, you can imagine loops that go around the tube, except in this particular tube, that loop is interrupted. But if you imagine the sides were closed, then that's the easiest loop to imagine. So if you imagine loops like this, then as this magnet falls down, the magnetic flux through this loop is changing. So so you have magnetic flux that's poking upward, and it's as this magnet slides down and moves away, it's decreasing in strength. So the change in flux is happening in the downward direction. This would be the change in magnetic flux. And Faraday's law says that if there's an electric, the line integral of electric field or voltage, that there's a voltage associated with the rate of change of magnetic flux. So there's a voltage induced around this loop. And Lenz's law, which is referring to this minus sign here, says that there's you can figure out the direction of the electric field this way. That if you imagine the current being produced by this voltage, induced voltage, then the direction of current is such that it opposes the direction of the original change in magnetic flux. So here, let me use one of my shortcut right-hand rules. So I want the induced magnetic flux to point upward. So I would want, as viewed from top, I would want my current to flow counterclockwise. So I want my current to flow maybe in this direction, counterclockwise. From this side, it'll be going kind of into the plane. Here it's coming out of the plane. Now, if you imagine a current loop that's going like that, then looking at that, you would say, oh, so current loop going that way, it's going to generate magnetic field that looks like this. These will be the magnetic fields produced by the induced current. And as you look at its induced current, or the magnetic field due to the induced current, if these magnetic fields remind you of magnetic field of a magnet with the north pole at one end and south pole at the other end, then that should remind you of that. That's what they look like. And in mechanical terms, this is what's happening. This south pole end is attracting this north pole end, slowing down the falling magnet. And you can do this kind of analysis consideration for any loops within the conductor that's surrounding this moving magnet. And what you'll find is that direction of this magnet will always be oriented in such a way that it opposes the motion of the magnet. The permanent magnet that's causing the original change in magnetic flux. So if you did an analysis like what I'm doing up here, analysis for this loop will show that, oh, it's not north and south, it's south and north, so that the south pole is repelling the south pole and again slowing it down. And it happens for basically all the geometries that involves a moving magnet near a conducting material. So that's why we give it a special name, because it's not the specific geometry that's important, it's the effect. Effect is that it produces eddy current. We call it eddy current because if you visualize the current within the body of that conducting material, it looks like the water eddies, and directions of those eddy currents are always such that it mechanically slows down the magnet. So that's what this demonstration is showing, and that's so with these induced currents, the magnet is being slowed down, which is why you are seeing it takes so long to slide down that relatively short section of the copper tube. I think I had a couple more demonstrations with this video. Let me just play through. Oh, I think I want you to slide both of them down together. One of them is a ferromagnetic, so they do stick together. But it's overall heavier, so it falls down faster. And I think I want you to give you a little bit of a closer up, so that will be the next segment, and then we'll move on. Just the magnet, not the ferromagnetic slot, just magnet. So slow I can just move it up to accommodate falling.
So yeah, so that's the eddy current demo. If you wanna play with this, you can. And in the lab today, what we are going to look at is an electric motor. And technically, actually, we could have introduced the electric motor much earlier because it's based on this magnetic force. But there's a reason we delayed it until now to introduce electric motor. Because to fully understand it, you actually do need the Faraday's law. So you'll look at that in the lab. Yeah, I think I covered it for your lab. So, any questions, comments? What I want to show now is it's kind of an electric motor. You can look at it that way. This can operate as an electric motor, and I guess I will show it working that way in a few minutes. But this is sold as it's sold as a generator. So let me first show it to you working as a generator. Let's see, how did I want to do this? I think what I need to do first is I need to stop sharing my screen so that the video is relatively the big thing, and so that I can also look at my own video. And I'm going to be switching my camera at some point so that I can change the angle and show you some of the demos that it's easier to place on the desk. So I guess what I want you to see is that the construction of device is really simple. Let me switch the camera now, actually. I think the external camera that I normally use, it doesn't autofocus. I disabled it, and it doesn't work well when I have the device I want to move back and forth. So this is the device, whole thing. It's connected to some wire stuff at the end, but it's a fairly simple thing. And if you have seen any electric motors, what you see at the end here might look similar to electric motor, as in this thing in the middle, that's the shaft of the motor, and you can't see inside the construction, but if this looks familiar to you like an electric motor that you might have seen elsewhere, well, it is an electric motor. It's got these wires connected at the end here to the two terminals. That's the wires that are connected here. And so why am I calling this a motor? Isn't this a generator? Well, it is a generator. It's not a generator. So let me show it to you working as a generator. Let's see here. Gonna bend. Okay, I think I need to put this way out here. Okay, so I have these light bulbs. Wait. Yeah, let me connect this generator to, so the leads of the generator to the two ends of the light bulb. And I'm going to make sure, this has two output modes, one low output, high output. I'm going to make sure that I put it on the high output mode. Why am I connecting this? I'm going to connect it closer because it's easier to connect it that way. Sorry, slippery. Wow, this is so slippery. Maybe it's because I'm using my left hand. It's like trying to use chopstick with your left hand. Okay, so I have the leads connected here, and I have this thing that's sold as a generator. So let me turn it, and yeah, it's a generator. Yeah, it's on. Yeah, it's on high output. So on high output, and on low output it works as generator too, but it kind of limits the current. So yeah. So anyways, high output. Yeah, it's a generator. So then why does it look like a motor? It's because it's also a motor. So that's why I have two of these, so that I can show it to you, working as a motor and a generator. So I have two of these now. I guess I'll leave the camera angle here so that you can see both of them reasonably well. So the one on the left, they are here. And I'm just going to connect the two of them so that one of them can work as a generator and the other can work as a motor. So I'm gonna, I guess the direction doesn't matter too much. It just will change in what direction these things turn. But let me just, for visual, I don't know, satisfaction, I'll just have the same colors the black wire to the black, red wire to red, but they can be up the other way around. It doesn't have to be the same. And let me make sure they are both on the high output mode. This is on high output, and this already was. So I'm gonna let me take the thing that I was before using as generator, and I'm gonna turn it. And as I turn it, this is what happens. So this is what I mean by saying that this is also a motor. So when I turn this, this works as a generator using Faraday's law to generate current here because there's an induced voltage. That voltage drives the current. And when the current goes into this motor, then that motor, there's a torque on the current carrying wire in there, and that torque turns this thing in the shaft, and there's a whole set of gears that turns the crank. So when I turn this, the thing here turns. Now I can reverse it. And by the way, you can kind of see that these two are not connected one-to-one. When I turn this fast, you see it turning, but watch when I turn this very slowly. When I turn this very slowly, making sure, I'm not generating so much current that it can't, so it's not a one-to-one relationship. It's a mechanical energy to current to mechanical thing, and there's enough losses there that if I do this slowly enough, that I can turn this without that other thing turning. But if I do it fast, then it turns. Now, let me put down my generator so that it can now be motor, and turn this motor so that it can be generated. So yeah, it's and I think your textbook doesn't give it enough emphasis. Every motor is a generator, and every generator is a motor. That's just how it works by the physical principle under which motors and generators work. That it's like there's no way for a motor to also not be a generator if you reverse the direction in which where the mechanical energy is input versus where it's coming out. Every motor has to work in some sense, or it should be capable of working as a generator. And I don't know, I guess I'm not 100% sure if it's, you can always, break it. You can put in ratchets and whatnot. You can make it so that it can go the other way. But unless you take effort to disable it somehow, every motor by design or every motor kind of by default can function as a generator. It's a two-part lab. One part deals with, or I guess it's got two different sets of equipment. One of them works with what's called the world's simplest motor. That's the kit provider's name. I think if you just Google search world's simplest motor, you'll find that. It's this. And I guess in the instruction, they had the people using battery body to have this coil of wire. That's what's important. And with the coil of wire, with the end stripped a little bit, you can have this arrangement. This is the magnet placed here. This coil of wire hanging over a magnet, connected in such a way that it'll be connected to a battery. It turns like a motor. So it's a motor, and it's the world's simplest motor because it is the fewest part you can imagine. Now it's a bit of I think in marketing legal terms, it's called what? Puffery. It's not the simplest motor. In fact, I believe homopolar motor is even simpler. So this is the lab working with these two simplest possible arrangements that illustrates magnetic force on a current carrying wire. And if that's the only thing, one might ask, so why didn't we do this earlier? We were covering magnetic force like 3 weeks ago. So we could have done this earlier. Why now? Why now is we needed the Faraday's law
to describe some of the restrictions on the operation of a motor. So that's why we are, yeah. And I think one of the questions get at that. Yeah, something like the two different questions. One about the measure the frequency of rotation, and question of what parameter limits how quickly the motor can turn. And in the lab, as you're doing the experiment, you would find that it's the voltage that that determines the turning speed of the motor. If you increase the voltage somehow, then it'll turn faster. If you decrease the voltage, it turns slower. And the and that connection can be explained the best using Faraday's law. And the other question gets at that when you are looking at this arrangement with a battery in here, a wire connecting one end to the other end of the battery, it'll look like we have shorted the two ends of the battery. In fact, the homopolar motor, yeah, we are shorting the top to the bottom. And if you remember when we were doing circuits, that's the one thing I tell people not to do. It's a safety hazard. And so this question is getting at, why is that not a safety hazard when you do it with a motor? And the reason is Faraday's law, induced voltage. And in fact, the thing to be careful with when you're working with a motor is that if you somehow brought the motor to a stop, apply a torque so that prevent it from turning, that's actually dangerous for the motor. Because at that point, you no longer have induced voltage that's opposing the voltage of the power supply, and you might have a situation where too much current flows through the wire and causes other damage to the motor. So yeah, as long as the motor is running, it's safe. The current output is limited, and yeah. So let me start out with the demonstration of these two setups. You've heard me describe them now, but video is a lot better than my words. So let me just show you the operation of the motor. Okay, let me change my share setting. So this is the world's simplest motor. I want you to show you the individual parts. This is the plastic holder that holds everything. There are the electrodes that go on the two ends to connect the battery to the wire. Yeah, I fiddle with it for a bit to figure out which way it goes. And that's the battery. It's used for two different, as a cylinder reference and as a power source. So anyways, I'm gonna and the magnet. I'm gonna put this away. I already assembled it because I want it to be short. And what am I doing? Oh, I want you to show the electrodes for some reason. Okay, that's the coil of wire. So it's enamel coated, so it's insulated between each loop. Now, at the end, if you look at it carefully, you'll see a little bit of a sheen. That's where the enamel has been stripped off. Now, it might look like it hasn't been stripped off uniformly, and that is on purpose. If it's stripped off perfectly uniformly, then the motor shouldn't work technically, because basically the net torque over a whole rotation adds up to zero. Now, in experiment, it turns out not to really work out that way. Even if you strip it all the way around, it still works. I imagine because the electrical connection we make is such a poor connection that as the thing turns, there's enough asymmetry that it still works. But anyways, the kind of instruction is to strip one side, and you want to kind of figure out when the stripped side is in contact that there's a torque on the wire. So that's what I'm showing in the video, the stripped portions of the wire where electrical contact will be made. You might say moving a little bit funny. Sometimes you need to give it a little kickstart so that it's not stuck in a dead zone. Yeah, there it is. World's simplest motor. And it'll basically run in that configuration indefinitely until the battery runs out. It could run for quite a few number of minutes, or I don't know how long. Yeah. So, and so here I'm trying to do something to demonstrate something, but I don't think it really worked. I want you to measure the voltage at the two ends to illustrate how the voltage of the battery measured while the motor is running is different from voltage measured when it is not. In fact, that's how people measure the frequency of that rotation with the oscilloscope, not digital multimeter. But this didn't really work out because let me just skip ahead. Because when I remove it and do it without the wire, it's so I think it's just a bad contact. So anyways, let me just skip this portion. It didn't end up demonstrating what I wanted to demonstrate. And I'm just trying to get the motor running again. In the future, I'll probably resplice this video so that I can just. But this is the world's simplest motor. That's all the parts there is. I think you can buy the kit for like $5 or $10, pretty cheap. And you could swap out this magnet here for a better magnet. I've tried it with a stronger neodymium magnet. Didn't work out all that much better. I think maybe because it didn't work out that much better. I think ideally you want uniform magnetic field over the entire region. And when I describe the working parts of the motor in a little bit, I'll be assuming basically the whole current carrying coil is in a uniform magnetic field, which is not the experimental setup, but big huge magnets are expensive. So, and this kit is a very cheap kit. That's what it comes down to. Okay, let me show you the homopolar motor. I think that's less commonly known, so it'll be fun. It's also very simple. It has a battery, AA battery, and it's got magnets at both ends. It doesn't have to be. It can be just magnet on one end. I just wanted to put, because these magnets are actually playing one more role in this demo. They also serve as a conductor. The coating that's around the neodymium magnet, it's electrically conducting. So the magnets that's stuck at the bottom basically provide a surface of contact for electrical contact. And this washer up here, it's not necessary for any electrical or magnetic reason. It's necessary for a mechanical reason. I'm going to place the wire that in this well so that it doesn't fall out as easily. So that's the whole setup. So I have a bar magnet with a source, with a voltage source that can provide current for the wire I'm gonna touch. That's one part of the homopolar motor. And this is the other part. It's just a piece of wire. And I guess one difference from the previous one, so it's gonna take a few tries. I'm gonna skip through some of these minutes. So the one main difference of this wire from the previous wire for the coil that you have seen is that this is not coated. It's not enamel coated. The entire copper is exposed, or unless it kind of is. It had a bit of a tarnish on it that I had to sand the paper off, but it's meant to be just conducting all throughout. So when this portion touches this top, it'll be electrically connected to this a positive voltage end, and when these two wires touch this bottom, it'll be electrically connected to the negative voltage end, or the lower voltage end. So the most challenging thing about homopolar motor is the kind of mechanical stability. It's basically a clothes hanger that's just hanging. So I'll show you a couple failed tries, and the way the wire moves weirdly, that is actually a magnetic force that's pushing the wire, except I didn't want it pushed that way. So let me just skip ahead a little bit. There's a attempt that worked even. Okay, that attempt worked. Okay. So as I make the contact, so okay, there. So there's a contact made at the top. So the current is flowing from this top portion to the bottom portion here. And as the current flows is where the magnetic fields exert magnetic force on the current carrying wire, and the whole thing becomes a motor. It's called homopolar motor because that's the design of this arrangement that's different from the other motor you have seen. In the other motor, we had to deliberately make the electrical connection asymmetric so that basically the pole of the electromagnet in the coil of loop, that pole switches. So the direction of the magnetic pole that's produced by current is changing as it turns one full turn. In this arrangement, it doesn't change. The direction of current stays constant throughout the entire revolution. That's why it's called a homopolar motor. So let's see. Yeah, so this demo is not the best. The bottom support kind of came off, but you can kind of see it work. Every time this wire makes a little bit of contact, current flows a little bit, so it pushes the wire a little. It goes on for a while. It might have actually gone on that way forever if I didn't stop it. But I wanted to. There was one arrangement that worked a little bit better in terms of getting it to spin faster. I think that attempt is towards the end. Let me just check this one and then I'll. Yeah, I think I'm gonna. Yeah, okay, skip ahead. Maybe that one. Oh yeah, that's the one. I mean, so it's not mechanically super stable, so eventually it pops off. But let me see if I can. Okay. I think in this view, I have access to this advanced control to advance it frame by frame. So what I'm doing here is kind of difficult to. Okay. So when the contact is made, then it's gonna spin. Okay. Okay. Now here, I actually don't know the direction of the magnet because these neodymium magnets don't come. They don't come labeled, but I think I can actually figure out the polarity of the magnet from observation of how this loop is spinning. So okay, I think this is a good view to kind of draw pictures on. So let me just draw some pictures. So I know the direction of my battery. So my battery has positive end here, negative end here, which means the current in this wire is flowing from here to here. And this is the way let me draw the other current as well. So I can do this analysis for one side, and the other side would be basically identical in terms of the directions and whatnot. So as we imagine looking at it from top, the direction in which the loop of wire is spinning is counterclockwise. So I'll just make a notation here that here the velocity is into the screen, here the velocity is out of screen, and it's kind of spinning this way, but that direction makes sense. Okay, so I gotta figure out. So here, do I want the magnetic field? So in this portion, I want the magnetic force in the direction out of the screen. Here in the direction into the screen. So that's the direction of force I want. So thumb pointing out of, and the expression for magnetic force for reference, magnetic force on a current carrying loop is IL cross B. So my direction of thumb, I want it out of the screen. My direction of current, I want it. So current is going that way. Okay. Current is going that way. Force that way. So I want my magnetic field to be pointing downward. So if my magnetic field here is mostly pointing downward, that's what. So let me just make sure that it makes sense. Yeah. Okay. So I want the magnetic field in this region to be pointing downward. Then if you go through the same analysis here, you'll see that magnetic field pointing downward here will also result in, L cross B, results in force pointing into the screen. So, okay, I think I'm almost there. So all of that means my magnetic pole at the top must be the south pole, so that magnetic fields are pointing kind of towards it. And my magnetic pole at the bottom must be north pole. And when I stock these neodymium magnets, I made sure they were all oriented the same way, so that they are adding to each other's strength, not subtracting. So with that determination of poles in mind, what the magnetic fields actually look like will be more similar to magnetic fields of a bar magnet. So something like, I gotta be careful, something like this is what the magnetic fields look like. Now, in terms of the relative orientation of the magnetic field and kind of direction of the wire, it's they're not nice 90 degrees. They are all at these angles, so you can see that it's not gonna be super super efficient. And there are big sections of the current carrying portion that it's either not in the so as when I imagine the magnetic field due to a dipole, I can imagine outward going magnetic field that's going to be causing some force on this section of current carrying wire. But I think there will be a kind of a pairwise symmetry. And since the current is in the same direction, that, oh, you know what? This is probably what's contributing to the loop just flipping over. I think, maybe. I don't know. But, there are portions of wire that will be in a region of magnetic field that's going to produce force in the correct direction, so that there will be a net torque about this center of rotation. So anyways, that's the homopolar motor that operates kind of this way. The current flowing through the loop of wire, it's causing those forces to be exerted on the wire, so it rotates like this. But it'll pop out in a little bit. Let's see. Wait. Oh, I'm stuck. Yeah, VLC doesn't like this frame by frame thing. It gets stuck after a while. All right. Wait, is that stopping? Oh, no. All right. Just stop it all together. Okay, so let me just paste it here. So this is a kind of working model of a motor, and you saw it work, and it's a model in that it doesn't have a practical useful motor would have more parts. It'll have more magnets spaced out and coil spaced out in such a way to smooth out in how often the current carrying loop will feel the magnetic force. So that's what practical motors would look like. This model of a motor is much more simplified, so that it's easier for us to see the working components of this motor. So let me make this smaller because I want to grab. Let me grab just one other screenshot, because there are basically two orientation of this loop that's worth considering as we look at the operation of this motor. So these two snapshots are illustrating two orientations of the current carrying coil. Let me talk through the operation of this model of a motor. And I guess for the purpose of this illustration, I'm going to assume that the top of the magnet is north end. I don't know if it is. It might not be, but I'll just assume that it's north end, so that I have some way to draw a magnetic field in a way that makes sense in some way. And even though in the real physical picture, I have only this tiny small magnet. So my actual magnetic field looks more like this kind of a dipole magnet. That's what my real magnetic field looks like. But for the purpose of discussion, let me say that let's just suppose that we have a region of uniform-ish magnetic field that's over the entire current carrying coil. Again, this is not quite realistic. It's not, or that's not how the actual physical demo is set up. But for the purpose of talking about what's happening with a motor, all we need is a uniform magnetic field. We don't need that it be a dipole field or that it has some spatially varying component. Nothing like that is necessary. So I'll just describe a uniform magnetic field, the simplest setup that we need for this motor to work. So in the simplest illustration, we can model the current as a single loop of current. So the way the actual physical demo is built, it has multiple loops, but that's so that there's a greater magnetic force. We are going to be talking mostly about direction, so we can just say, I think this is the positive end. So, oh wait. I want to be careful with the direction. Let me do this. I'm just going to draw a direction of current. And if it turns out that I messed up, assuming that this end is north, I'll just reverse it. So looking at here, I have, let's say, I have current coming in from here. And let's just say current is flowing this way. And it makes some loop. And then eventually goes out this way. So that's the direction of current. And let's assume some similar direction here. Current comes in. And I'm going to say on this end, it's going into the page. So goes around, around, around. And here it comes out of page and then goes this way. Okay. So the direction of current here would be flowing that way, this way. And the far side is flowing that way, near side is flowing this way. Okay, so that's the arrangement for this motor. And what a motor is, a torque exerted on a current carrying wire by magnetic field. That's really all that's necessary for the operation of motor. So we can quickly analyze what kind of torque is exerted on this current carrying loop by this magnetic field. Let me draw copy an illustration of that here. So I have a coil with I'm gonna imagine a more rectangular kind of coil with a segment that's going into the page and a far segment that's flowing left to right, a near segment that's flowing out of the page, and then or the segment that's coming towards us, and a segment that's going from right to left. And then the loop goes however many times, and then current eventually goes out. So this is one current carrying loop, that's a version that's there. So when we have magnetic field in the region, so we can do the right-hand rule to figure out the direction of force on each of the segments of this wire. So let's do that. So the first segment I'll consider is where current is flowing into the screen, into the page. And I want it so that magnetic L cross, so I'm using this expression that you have seen before, that magnetic force on a current carrying wire is current times L cross B. So the direction of L is into the screen, and I want my hand to be oriented so that when I curl my fingers, they can curl, up towards the magnetic field. So my force is rightward for this segment of wire. So I have a rightward force here. Okay, let me just double check from my perspective. Okay, and the segment that's farther away from us with the current flowing from left to right. So left to right, cross B. So left, no, that's right to left. Left to right, cross B. Okay, so there are magnetic forces coming out of the page. So let me just do that and just double check that you're good. And here with the L coming out of the screen, L cross B. Okay, so the force is to the left. That's the direction. I think I can kind of guess this one. It's probably gonna be this. Let's just double check. Current is flowing from right to left, cross B, and yeah, magnetic force is pointing into the screen. Okay, so those are the direction of the force, and as you look at that, horizontally lying loop, if you are figuring, it looks like I'll have that net torque is 0, then you'll be right. These forces around this center of rotation, these forces have no lever arm. These two forces were never going to cause any torque. And these two forces, if this loop is horizontal, then the lever arm for these two forces are 0. They're just stretching the loop out this way. Stretching? No, they are compressing. They're just compressing the loop in this way, but they are not causing it to rotate. So this is one of the things to watch out with a motor. A motor of this kind of design has dead zones. There are orientations of the current carrying coil that won't produce any torque. And now with the more practical motors, there are things that people do so that motor won't get stuck in a dead zone. But with the world's simplest motor, yeah, that can happen. Can get stuck in a dead zone. So let's analyze the other orientation to see what it does. So for the other orientation, we have current coming in, and on the left side of the coil, we'll have current that's flowing upward, I think, yeah, upward. And then on the top segment of the wire, current flowing to the right. And I know it's a circle. I'm just going to draw it as square so that I can talk about the 4 sides with the 4 orientations. And the current flows down here, and then current flows right to left to here. And then after some number of loops, it leaves. Okay, so let's do the same analysis. We are figuring, okay, magnetic force is IL cross B. So and I'm figuring the direction of the force on each segment of wire, or each kind of orientation of wire on this circular thing. So for IL cross B, for the left segment, I have, so my current is flowing upward, and I want to bend my fingers in such a way that it can bend towards magnetic field, and I see that I can't do that. Magnetic field is also pointing upward. So around here, on this segment, magnetic force will be 0 in this orientation. Okay, let's keep going. At the top, where the current flows from left to right, so I want it so that IL cross B, okay, magnetic force is pointing out of the screen. Let me just make sure that looks correct from my perspective. Okay. On the right segment, I think the same thing's going to happen, because for this segment, the magnetic field is anti-parallel, and 180 degrees sine of that is also 0. So magnetic force here is 0 as well. Okay. At the bottom, I have current flowing from right to left, and magnetic field. So this is IL cross B. Thumb is pointing into the screen. So magnetic forces into the screen there. Okay, so these two look promising because they do now have lever arm. This is lever arm, and this is lever arm. So if you imagine this, these two combined forces will tend to rotate this whole thing in kind of this way. So if you imagine looking at this coil from a point of the observer who's over here, then from this observer, it'll look like it's spinning counterclockwise, I think. Yeah, so there, from this observer's perspective, net torque is counterclockwise. So that's the torque on the loop of wire. Um, so applied over some amount of time that'll cause the loop to rotate, and that's exactly what you see with this world's simplest motor. Now, I don't remember in the demo if it actually spun in this direction or not. If it actually went the other way, what it would mean is one or the other, which is it could be that the current was actually flowing the other way. I don't know. I couldn't track the direction of wire in this screenshot. Or it could mean that the direction of magnet is opposite. Flipping either of them will flip the direction with which motor runs. And in terms of the practical orientation, practically how this demo works, it would depend the direction in which it spins. It would also depend. Wait, would it depend on? It does depend on which side of this straight wire is stripped, because I'm supposed to strip only one side. So when the whole loop is in one orientation versus the other, so in one orientation, you can imagine it here. If I imagine flipping this around so that after it has turned 180 degrees around, then the current at the bottom is now flowing left to right, and the current at the bottom top is flowing right to left, then you can see that the direction of torque will flip. That's why you need a bit of an asymmetry. In a practical motor, they have something called either it's called the alternator or commutator, something that will flip the direction of current as the motor turns, so that the net torque is in a consistent direction. For our world's simplest motor, all we have done is introduce a bit of asymmetry, so that in one orientation there will be torque, and in other orientation there won't be torque, but the inertia will carry through, and the motor will, as long as the motor receives enough integrated torque over a full turn, it will continue to run, as you've seen in the demo. So that's the motor. Now, so far, so as you are hearing this description, if you are asking yourself the question, so why didn't we do this earlier? Well, yeah, you're right. We could have done this earlier, and here is why now we are. Here's why we are now talking about motor. Because if we had talked about motor before this week, then there's one aspect that we couldn't fully explain, which is this. So as you imagine this setup, as you imagine this net torque that's being exerted on the coil of wire, you might see that so you have this torque whenever the wire is in this orientation, and there's nothing kind of limiting. There's nothing that says as this thing spins faster and faster, torque should be less. And if you have a constant acceleration for an unlimited amount of time, you'll have a very, very high velocity. You could ask the same question if you have a constant-ish torque, which would lead to constant-ish angular acceleration in the counterclockwise direction for an unlimited amount of time. One could easily ask the question, why doesn't this motor speed up kind of without limit? Why doesn't this motor spin really, really fast? And And you might say, oh, eventually, the friction and whatnot is going to be too much. Okay, then why not the regular motors with the frictionless, friction minimize the bearings and all that? Why don't those spin out of control? And I guess with the more complicated motors, you could imagine that there's some kind of regulator built in. Well, they don't, but what they do have is nature's regulator. There's a secondary effect that will happen as this loop of wire spins. That's going to naturally limit how quickly this can spin. Imagine this loop spinning back and forth between these two orientations. I mean, it's not quite back and forth. It's turning 90 degrees each time. As it's doing that, something is changing with the loop. So with the loop in this orientation, the magnetic flux here is 0, because you can kind of see none of the magnetic fields are going through the loop. When the loop is in this orientation, the magnetic flux, well, it's not 0. Its magnitude is the area of the loop times the magnetic field. So as this loop spins, you have a change of magnetic flux. And as you learned this week, the change of magnetic flux, or the time derivative of magnetic flux, is associated with this line integral of electric field, which is, I could give this another name, a line integral of electric field is voltage. So this rotation of the loop itself induces a voltage in this coil of wire. And this voltage is always induced in such a way that it opposes this change in magnetic flux. So this is what your textbook calls back EMF. I'm trying not to use the word EMF, so let me call it, what was I trying to call it? I tried calling it back voltage for a while and it didn't sound right. Am I calling it reaction voltage? Not really. I don't know. I should just call it back EMF. That's the terminology your textbook uses. There's an induced voltage in this coil that's going to oppose the voltage that you are applying. So there comes some equilibrium speed where the applied voltage equals the induced voltage that's opposing that applied voltage. And at that point, the whole thing is not going to really draw all that much current. So if you imagine a frictionless, perfect coil of wire, a perfect motor that's spinning frictionlessly, then there's a kind of an equilibrium speed where the coil won't be drawing any current because the voltage you are applying is precisely opposed by the back EMF. Or in the case of a more realistic motor, the only amount of power that's needed to be drawn is the same power that's needed for the motor to do mechanical work, either against the friction or against the load that you are imposing. So this portion of this part of the operation of motor is important because this makes it so that a free running motor is safe. It has some natural maximum speed that it'll run to that depends on the magnetic field and applied voltage. So the applied voltage acts as a natural regulator. It limits how fast the motor can spin. And at the same time, if you want the motor to spin faster, okay, apply a higher voltage, and then it'll be able to spin faster. And this is again why it's dangerous to just stop the motor, because if you just stop the motor, then nothing, no longer the amount of current that can flow through the coils is no longer limited by something other than resistance of the wire. And if you just want a very low resistance wire connecting one end of battery to the other, that's a short. It can it can draw a lot of current, and that's dangerous. So simply stopping the motor cold is it's not something that you should do. So while the motor is running, it's perfectly safe because this induced voltage will oppose oppose the applied voltage, limiting how fast it can spin and how much current it eventually draws. So okay, so that's the lecture on electric motor that we really had to hold off until now so that we can discuss the full detail of everything that goes into operation of motor.